I really appreciate you having me back for another year, and I have to stop doing high-density talks, which has been pretty much most of my content for the last couple of years. So this time around, we're going to talk about multi-user MIMO. There's so much new that's happening with Wi-Fi, and it's exciting. Last year we were just shipping AC Wave 1 products had just been in the market for about a year, and we just kind of got to the point that we had a lot of experience with it, had a lot of good data we could share, and of course now Wave 2 products are shipping, and a lot of you have questions. I had a lot of questions. There's a lot of fundamentally different things. How does it work? What does a packet capture look like, and so on. So I thought it would be great to give you all, particularly those of you that, since most of you haven't had a chance to probably really play with it yet, to give you kind of a preview and share a little bit about what we've learned internally. And now I'm like self-conscious about logos. Thanks, Keith. So this is the only logo in this presentation. I'm not in marketing. I'm part of the CTO organization at Aruba. So the company is kind enough to fund the research or the work that I'm going to present. So that's appropriate that be up here. But from this point forward, it's going to be just all content. And I'll take questions. We usually make these interactive. I think Keith has given me a little extra time this year, so we have until 10:15. So if you've got questions as we go through, again, I expect pretty much everybody, most people here, MU is a totally new topic. And just to be extra clear, it's very new for us. We are literally just learning all about how to make this thing work and make it better. So we'll start with terminology and some basic concepts. I'm going to walk you through some of the highlights about how it works at layer 2, and I'll show you some very early performance numbers about what you can expect. It's pretty exciting, actually, and we'll take a look then at where some of the gains come from. You may have seen videos from different vendors starting to talk about multiples, 2.4x, 1.6x, that sort of thing. So we'll talk through where the gains come from and also where we lose some things and some of the dependencies. We're going to spend some time. I'm going to show you some data about sounding overhead and find a way to sort of work high density back into this presentation. And then we'll close out by talking about some early thoughts about how you should all be thinking or approaching new WLAN designs that you're preparing for yourselves or for your customers. So just a show of hands, who's been able to actually get their hands on MU equipment and do a packet capture? Okay, that's what I thought. Great. So good. By the way, that was my situation on November 1st. So everything I'm showing is work that we did pretty much in the first half of December. We bought 10 machines and then borrowed 10 more from QA, and we had a chance to actually sit and learn how to drive the car, right? So I wanted to, kind of in the spirit Keith was just describing, I wanted to kind of bring that knowledge to you. So just a quick recap. So features and terminology. So we got 3 new things with Wave 2. First of all, we got 4 streams, which isn't necessarily that new conceptually, but the leap from 3-stream to 4-stream came with Wave 2. Gives us a bump in the data rate for 4-stream configurations. And the trick here, though, is, as I've said in other venues, we are not expecting to see any 4-stream clients. You virtually can be assured that that's never going to happen. Even the 3-stream clients are probably going to trend away in the market. The market is really converging to 2-stream clients for the most part. There are just very few laptops you can buy right now that have even 3 streams. So we got MU, that's going to be the focus of the talk. And we also got 160 meg channels, which is kind of hilarious because we don't have the spectrum to actually deploy these, right? There's only 2 channels in 5 gigahertz to deploy right now. And there's a lot of questions about some of the additional spectrum that's coming. So this is a channel plan for what exists now and what might be coming. And So the solid red areas are channels that we hope to get from FCC in the US at some point over the next few years. But both of these bands are contested. So in the 5350 to 5470, there's a lot of government and military stuff in that band. And the current understanding is that the soonest those bands are going to come available is 2017, maybe not even until 2018. And you should expect that all the new spectrum that we get in any band is going to be encumbered by some kind of a sensing requirement. It'll look like DFS in that sense. Might be the channel vacating requirements might be a little different, but you can be virtually sure that the incumbents in these bands are not necessarily all going to go away, and therefore we have to defer. And then on the high end, the 5850 to 5925 range, that is allocated to the automotive industry. Great question. Yeah, question is, where's the box? Do we have? Okay, no boxes here. Yeah, the question is, do we expect that the radios will be retroactively configurable via software or what have you to support those channels? Generally speaking, I think the answer to that is yes. I can't speak for all vendors, but that's very much the intention of that we have. So if you look to my point about the two 160s, right? So this top row, you can see that there's 4 160s if we get all that spectrum, but without it, there's only 2. So 160 is really not viable, right? You can't roll out a 2-channel plan. Even in the 80s, we only have 5 80s right now as it stands, and there's more on the way if we get these extra channels. But anyway, so these are things to think about. You know, the technology is getting ahead now of what policy permits in the real world. Here's a view of European countries. So this is ETSI and all the countries that follow ETSI, and it's even more restrictive. We don't have the Uni 3 bands in most of Europe, so you know, it's even a little more challenged environment. Again, 2 160s and just 4 80s, right? So it's a 4-channel plan if you want to roll out 80 megahertz. Okay, some numerology, which is a fancy term that I've been going to IEEE for 2 years now, and it's a term that's used to describe how basically how you quantify aspects of the protocol. So I think everybody's familiar. Basically, the terminology we've become accustomed to, the 3x3:3 type thing, is going to get longer, because as is the data rate table, unfortunately, because in order to describe how some of these devices differ from one another, we need more nouns, basically. So everybody knows transmit times receive chains and the number of spatial streams, right? That's, I think, pretty well ingrained. So the 2 new numbers are going to be the number of MU streams, which may be different and is different currently on most products that are in the market. And I'll show you some examples here in just a second. And then the number of stations in an MU group, right? So in other words, what's the maximum number of stations the AP can communicate with at the same time? So here's some examples. And not to pick on anybody, these are simply meant to be illustrative. I'm not making competitive points or anything along that line, but it's useful just to sort of see what's in the market and then also look at the standard. So there's an enterprise vendor that has an MU-capable product that is a 2-stream product with 3 chains, and the MU to the final term. So the number of stations in the MU group obviously cannot exceed the number of MU streams, right? So that could be, and we'll work through some more configuration examples here in a second. We're shipping a product that is a 4x4 that does 4 spatial streams in SU, but 3 spatial streams in MU. And most of the products in this class are using the same hardware, the same underlying radio right now, so they're all going to have that property, which is why I've got the other ones listed. And then, of course, the consumer vendors, as everybody knows, tend to get in the market a little quicker and be out a little in front of the enterprise vendors. So there is a consumer vendor, actually there's a couple of vendors now, with a 4 MU chain AP, which can communicate with 4 stations at the same time. And of course, the standard permits 8 by 8 with 8 streams of SU, 8 streams of MU, and 4 simultaneous clients, right? Everybody with me so far? Okay. And you can see that why you need the 5th digit, right? Because otherwise it's not necessarily clear. This is the easiest way I've found to explain the deltas between these. So let's work through what does this mean in a real world in terms of the clients that you could be supporting concurrently in the environment. So that vendor B example I was giving before, so if my device can do 2 streams of MU, then the most I can support concurrently is 2 one-stream devices, right? Because I have 2 spatial streams, right? So I can send a stream here and a stream there, and that's pretty much what that product's capable of, right? And of course, more capable radios automatically can do that as well. Now, the next batch, the product that we're shipping and a couple of other companies are shipping right now that does 3 streams of MU, you get 2 more combinations. Now I can do 3 single-stream transmissions concurrently, or I can do 1 2-stream and 1 single-stream, right? So I'm not using the full MU group size, because I've run out of spatial streams, right? But I can use all my streams. This next batch, so this consumer AP that's just come out, that's the 4 MU. Now I get some other combinations. Now I can do 2 2-stream, 4 1-stream, or I can do a 2-stream and 2 1-stream, right? So again, it's the number of MU streams that you hit first, and then the number of MU stations that you hit second. These combinations are going to have to wait for a radio that does more streams, but these are all valid and permitted under the standard. Make sense? Okay. It's a little head twisting, but that's what we're dealing with. So just a summary, not going to spend a whole lot of time on this, but the maximum data rate now with 160 and so on is 6.9 gigabits per second. And so to get that, you'd have to be in a 160 meg channel with 8 full streams, either in an MU configuration or an SU configuration. You probably won't see that ever in an SU. It doesn't really make any sense. And we're looking at about 4.5 gigabits of throughput. And it's really, I mean, Wi-Fi has progressed, fantastically through the years. One of the, we were talking about this last night, one of the things that I think is we all as an industry, as a community, need to be pushing back on. There's this narrative that's getting established by the unlicensed LTE community that Wi-Fi is not dependable, Wi-Fi is not robust. You can't, if you were in a hospital and you were going to, for a procedure or something, God forbid that any of your medical equipment would be running on Wi-Fi, you can't trust your life to it. Well, nothing could be further from the truth, right? We just moved, hospitals run on Wi-Fi, right? Manufacturing plants depend on Wi-Fi. We just moved 10 terabytes at the Super Bowl. Wi-Fi is, when it's properly designed, and that's part of what you're all here about, is incredibly capable and can support incredible loads. And you're going to hear more about that from other people. So we need to be getting this message out that Wi-Fi is mission critical. Wi-Fi is something that you can, people trust today, they just don't realize it. That said, on the data rate front, because I said that the market's going to converge to 2 streams, these are basically the data rates that you can expect for a single client. So when you're doing capacity planning for MU, now you have to differentiate between what the AP can generate and what an individual client can do, right? As you're working with customers to set expectations. So if I've got a 2-stream client, right, running, and I'm close enough that I can get MCS 8 or MCS 9, the maximum PHY rate I'm going to get in an 80 meg channel is 866 megabits, right? Even if the AP can do 1.7, right? So as you're setting expectations, that's a conversation that you want to have. Okay, channel model dependencies. So multi-user is a superset of spatial multiplexing and beamforming, right? But it's different than beamforming in wave one. In wave one beamforming, we're sending all the energy in one direction, right? Trying to increase the gain to a single client. With multi-user, we're sending energy in multiple directions, and I'm peaking, station A, and I'm trying to null the other station. So I'm actually dividing the power up in a different way. So I need beamforming, and I need spatial multiplexing. So how many spatial streams can I get? Which of those data rates am I actually going to get in the real world? So in the wave one world and back in the 11N world, we all learned some things about MIMO, right? We learned that low ceiling, basically high bounce environments are absolutely give you the best spatial stream rates. If you just look at what in Windows or Mac, whatever data rate you're getting, right? If you're going to monitor it, and so low ceiling, tight walls like this give the best rates. You go into a warehouse, right, or something, or an arena, something that's a little more open, you're probably going to have a little harder time maintaining the higher rates. And then outdoor, because we don't have a whole lot of bounce at all, is generally limited to two-stream operation, and except potentially in the mesh case where we can get beyond the 200, 250 meter limit with special antennas. So how many MU users can an AP realistically support? This is one of my sort of main questions back in November. So what basically the vendors told us that we talked to the silicon vendors and then basically saw this in our own testing, that a quick check is what's the maximum data rate you can get with an SU machine? Can you get 3-stream SU rates? If so, you can probably get 3 MU streams. If you can't get a 3-stream SU rate, you're not getting 3 MU streams in that environment. So that's just a quick sanity check on that. Walls and impairments, don't know. It's too early. I haven't been able to test it yet, and I haven't seen any. In general, there's not much data that's public yet. Okay, so that good level set for everybody on background. So let's talk about the layer 2 operation. So the TXOP structure for MU changes significantly. So it used to be that we had, if you saw my talk from last year, we had RTS, CTS, MPDU, and block ACK, right, was the structure. But now the AP is talking to multiple clients, and the only part of that entire conversation that is multi-user is this first section, which is the AMPDU, which is, for those of you that, so how many people have a CWAP or have studied protocol? Fantastic. Okay. And that's huge growth over last year. Yes? Sorry? Sound? Can we bring up the sound? Or maybe, oh, okay. Maybe the mic shifted. That's on. Is it louder now? Okay, thanks. Yeah, that's fantastic. And how many people tested? Were we doing tests here? We're just, okay. All right. So anyway, so this is the basic structure, and there's an implicit block ACK request after the MPDU. So the first station in the group is going to send a block ACK, but then the AP has to poll the other stations in the group, right? So right away it starts to get more complicated, and all of those other frames are single user frames, right? So it's preceded by arbitration, right? So we have to get the channel, right, through the usual process. The actual data payload itself can be a mix of different MCSs. So each station that's in the MU group, they don't all have to be the same MCS. It can be a mix. The MCS will be reduced, as I'll talk about in a minute, because I'm dividing the power, right? It's not like beamforming where I'm aiming all the power in one direction. I'm splitting the power up. Therefore, the AP is probably going to have to drop the rate down, right, to compensate for that. And then all of these are standard control frames that are sent at the lowest basic rate. Okay. So there's a whole lot of SU transmissions to allow that one MU exchange to occur. And we'll dig more into that as we go. So We'll talk about channel sounding next, but just as a quick recap, so here's what a Wave 1 sounding exchange looks like. So we've got this thing called a NDP announcement, or null data packet announcement, and then CIFS, and then this thing called a null data packet, which is really not a packet. That's why it's called a null data packet. It's just the purpose of the frame is to allow the receiver to essentially calibrate the channel and report back what it saw. So it's just the preamble and it's the training fields. There's no actual content, or there's not even addresses in it. And then the receiver sends this beamforming matrix back to the sender. So that's how it worked in Wave 1 when I was trying to beamform to a single device. Well, now with Wave 2, of course, before I can do the MU transmission, I have to understand the channel state to all the stations that I'm about to talk to, and that channel state varies on a much more rapid time scale than it does for beamforming. In Wave 1 beamforming, the channel coherence time is on the order of 100 milliseconds to, it's hundreds of milliseconds, I guess would be the best way to describe it. With multi-user MIMO, the channel actually degrades much more rapidly. It's on the order of tens of milliseconds. And so the AP has to continuously re-probe the channel to understand the current conditions. So again, we see, so there's no MU in this exchange at all. It's 100% SU. And most of this is going to go at the lowest basic rate. Again, the NDPA, the beamforming poles, these are control frames. The NDP itself, because it's preambles and training fields, is sent at BPSK. And then the beamforming matrix itself, or it's called a compressed beamforming action frame, this is sent, it's data, it's a payload, it's information. So it's going to go at an MCS rate. And by the way, if some of the terminology that I'm using, MCSs and these other things, if these are not, so the NDPs and so on, if you don't have a CWAP, or if you haven't started to move down that track, grab any one of the CWAP reference books and curl up with it for a weekend, and it's fantastic training, and it's just really good fundamental knowledge. The shameless plug for a few authors in the room, but seriously, we as a community, we need to all raise our foundational knowledge about Wi-Fi. It'll make us more effective engineers, it'll make us more effective architects, and so on. And nobody teaches this. You have to choose. You have to seek this information out and choose to study it. But you won't regret doing it. So anyway, this is a payload frame, and they get pretty big, as you can see here. So it sounds like this will be the first MU PCAP that most of you have seen. So this is the sounding exchange at the beginning of the transmission. And you'll notice I said there was an NDPA, but there is no NDPA in the PCAP because it's invisible, right? Can't see it. There's nothing for the driver to pass up. Then here are 4 MU TX ops, right? Or MU data transmission. So that's the first thing I was showing you. And you might say, well, how's that? Where's the data, right? I just see block ACKs and block ACK requests. Well, here's the data. Right? There are no Wave 2 packet capture machines right now. So you can only capture with Wave 1, which means you can't decode the transmission. So the signature is the jump in the delta T before in between the CTS and the first block ACK. Right? So that'll change in time, but that's what you have to deal with now. In my capture, we're actually running a higher basic rate, so we took out 6 and 12 and 18, and I've got 24 as the minimum, so that's the reason you're seeing these control frames at that rate. That is intentional, and I'll close. Remember this when I close, because we are recommending, again, you've seen there's so much SU transmission, so in some senses, you want to do high-density rate practices for SU-MU deployments, or sorry, for MU deployments. Because the SU frames are going at these low rates, right? So you can actually get more capacity. There's so many more SU frames on the air with MU that you really want to bring the rates up. This is OmniPeak. Sorry, the question is, what did I use to capture this? So the display is OmniPeak, and then the actual capture is with a MacBook Pro. Yeah, using the wireless diagnostics. I'm going to talk about that in a couple of slides. Yeah. Question is, how often are sounding frames being exchanged? Hold that thought. I'll tell you later. I've got data on it. Oh, great question. The question is 24 the maximum I'm recommending right now? Not necessarily. I think it's a safe high. It's a safe high starting number. You could go higher depending on the environment that you were in, right? If you had a very favorable channel model enterprise environment, you could probably go to 36, but 30 above 36 would be pushing it, I think. Yeah, sorry, John. How are the clients selected? So that's a decision that the radio makes. So it's in the firmware. I'm actually not that far in terms of understanding the group. It's a combination of, first of all, who's got data to send, what is the channel, are the channel conditions favorable after the sounding, and then other factors, right? We don't necessarily even know the recipe at this point. These are proprietary algorithms that the silicon vendors make. Yeah. Okay, look at the size of the CBAF frames. 1,499 bytes. This is in an 80 megahertz channel, and a little later we'll dig into estimating the size of these frames, but that is enormous, right? Typical beacons are what these days? Yeah, about 300 bytes if you're not running Hotspot 2.0, right? That'll add another 100 bytes to it. So, this is 5 times heavier than a beacon, and there's 3 of them back to back, right? For a sounding, and they're going at a low rate. It's 29.3, but they're payloads, so they get an MCS, but that's MCS 0, right? So it takes a lot of airtime to transmit this stuff. Okay, sounding interval. So we'll start to get to the question that was asked earlier, but we're going to really dig into it later. So in this particular exchange, this is a different exchange. So this is what you look for. These blocks of basically control and management frames. And in this case, the sounding interval is about 16 milliseconds. This is in the middle of a chariot test, right? So you would see this repeating over and over again. Okay, so what does it look like? So now you've seen a trend, a TX-op is a term for basically its transmission opportunity. It's shorthand for a single transmission that would include all that stuff that we just talked through, right? So now that you've seen a single transaction, is another way to think about it. So let's look at an actual test. So this is a view in OmniPeak. You can do this in the tool of your choice, but this is a perfect MU packet capture with a 30-second IxChariot test where we pumped about 865 megabits per second of traffic. You're wondering where the data is. This is a training period, and the reason, and I'll show you stuff behind this here in a minute, but basically we're seeing traffic on the air during this training period while the radio is basically figuring out the environment. And then this is what I'm calling a pure MU transmission. And the reason you can't see anything is that we can't decode the payloads, right? So perfect MU with the current capture tools is blank, right? Except for that little thing at the bottom. That's all that SU traffic. That's all those control frames that are going on. So you can see just kind of very sliver. So by the way, here's what the Chariot console looked like for that test. We pumped 800 and we peaked at 890. The average was 856, and I've included both the aggregate on the top and the 3 individual stations on the bottom. Right. Yeah, Sam, go ahead. Yeah, so is a hardware issue that could be solved in software, or you need a Wave 2 capable sensing device, whether it's an AP, could be a laptop, just something with a Wave 2 NIC that has a packet capture driver that would support it. Yeah. So obviously, sorry, go ahead, Daryl. Yeah. So the question is, how does this affect the clear channel assessment if the frames are not decodable? So there's a CTS at the beginning of the transmission, so that the channel is protected for the duration of the TX-op. So that will clear any station, regardless of its phi. Okay, keep moving. So here is a mixed test. This is so this last one was 3 stations, 3 stations, 1. So we're not doing. There's no group thrashing. So here's 10 stations, 1 AP, 30-second chariot test, and now you can see it's a little messier as compared with the last slide. And the reason for that is that radio is having. I can only talk to 3 stations at one time, right? We talked about that earlier and what the capability of this particular generation of radios is. So to talk to 10 stations, we picked this on purpose, right? So that's really, I can't do that in even 3 groups. So the radio has to be constantly shifting between the stations that it's communicating with. And so some are going to fall out at any given time. So we start to see a little bump up in the SU transmissions. So there's actually SU data payloads that are getting on the air here for various reasons. And the training period is a little longer because there's more stations to talk to. Okay, so I mentioned earlier that the rates are reduced. So we can't see this now? Yes? Do I have the aggregate? I don't have it here, but I'll show it in a couple slides. So I said earlier that the rate is going to be reduced because of the MU is splitting the power up to different directions. So when I reduce the power, I'm also reducing the SNR on the link, right? Because I'm ultimately capped by the regulator, right? We can't go higher than whatever the power is that the AP is approved for in the domain or certified for as equipment. So reduced power, by definition, means reduced data rate. So you're going to see, when we do get Wave 2 capable packet capture sensors, you're going to see that the MCSs during the MU transmissions are lower, right? So if you're getting MCS 9 SU, you're going to get MCS 7 or 8 MU, right? And on down the list. Great question. Is all the complexity worth it? So I was, part of the reason I went down this road is I didn't know. I was really curious. And particularly, since you all know I do a lot of high density work. So I'm particularly interested in high density, right? And do we turn MU on or not? Right? That was really the question in the back of my mind starting all of this. So stay tuned. Okay, so how do you get MU payload frames, right? We talked about this. So basically, in addition to what we've just talked about, where do you put the capture machine? If you're splitting power to different directions now, and particularly if you're in an SNR challenge condition, right? Do you put it at the AP? Do you put it at the station? If you put it, and we're peaking and nulling, right? So the station that, if I'm station 1, I'm peaking and I'm nulling stations 2 and 3 for those spatial streams, right? And vice versa all the way down the line. So if I put the packet capture machine next to station 1, am I going to be able to pick up the spatial streams going to 2 and 3, right? So there's all kinds of interesting stuff. And also we need new analytics. There's all kinds of new reports. Like we found that it's really inadequate, right? The current SU, all the charts turn out to be biased towards SU operation. And there's questions you start to ask once you start doing MU PCAPs that the tools just aren't built to answer. So we're working with the various providers on doing that, and they're starting to think about these things. So a couple of you have asked how to do it. So basically there's 3 ways. You can do it with an AP. The AP has to support packet capture and has to support streaming that PCAP to a remote Wireshark or OmniPeak or whatever you're using for the frames. It has the issues we just talked about, and you have to carry an AP around, basically, to do this, right? So it does work. This thing, though, I want to point out, the split MAC may conceal the MU frame. So depending on the architecture of the particular product you're using, some of those frames we were just talking about won't make it back to the controller, or may get eaten if there is no controller, right? They may get eaten by the driver, right? They may not be exposed. So if you're not seeing everything I just showed you, that's probably because of this issue, right? So that's going to be implementation dependent. The MacBooks, if you're not using MacBooks for capture, this is really the bomb. They're very portable. Apple has a built-in. If you haven't used it, there's a wireless diagnostics function. It'll do PCAP automatically. Just save it to the desktop, and it's relatively lossless. So it's really dependable. The downside is you can't stream it, so you got to backhaul it to your capture machine and analyze it. USBs, very lossy, no Wave 2, obviously. You're going to be limited to about 2 streams in any, so you won't be able to see a 4-chain, 4-stream environment. But USBs are indispensable for roaming problems, right? You can still load up your, 8 NICs on here with your USB sticks and everything, and then follow a device as it's roaming, but probably not so helpful for MU. I'm sorry, I can't. Oh, what do I mean by lossy? The USB, you just missed frames. The processing power of the USB sticks is not that great, and then you're bound by the bus speed and so on. So we find that they're very, very lossy. If you capture with all 3 methods, and we've done this for the same exchange, you'll find that you're missing a huge number of the frames with this method. Yeah. Okay, performance. So let's see some numbers. So just a disclaimer, again, I'm in CTO, I'm not in marketing, I'm not trying to score competitive points. My goal is to just give you some sense of what's coming, and to Jason's question earlier, it's pretty exciting stuff. I didn't know what to expect, honestly. While the numbers are good, they're going to get better. Every vendor is working hard and independently, and then also with our silicon suppliers to get these numbers even higher and to optimize the channel sounding and so on. So cut us some slack as we go forward, and you should expect to see that numbers are, vendors are probably going to trickle out lower numbers of stations earlier, and then we'll scale up to larger and larger stations as this gets done. But this is true of every Wi-Fi generation, right? Every wave, N was like this, AC wave 1 was like this, and so on. We really want to build excitement, and then obviously one point of the conversation is to help everybody understand the trade-offs in the environment. So here's some of you have seen pictures of my lab before. So we bought basically 20. These are Acer laptops with 1-stream MU cards in them. We bought the 1 streams intentionally because I didn't want to be evaluating mixed stream performance just yet. We wanted to just keep it simple and basic. You throw some APs up on the ceiling, and you'll notice we put them in a straight line. So another question that's out there is, do you have to, does one have to be on the left and one have to be on the right? How does placement matter, right? How sensitive is MU to the actual placement of the machine? And we found we were able to actually get pretty good MU in a linear configuration. We also took it outdoors because we have a running debate about whether MU can be achieved in outdoor channel models. And it's just fun to do on a Friday. Okay, so numbers. So this is out to 9 stations, and the orange curve on the top is indoor. The one in the middle is the outdoor numbers, and the one on the bottom is we tested in just SU mode as well. So the SU number, let's go bottom to top. So the SU numbers, about what you'd expect, 350-ish. This is UDP. So we're looking at a multiple, right, that is well over 2x. For the 3 client case, and then starting to dip. Again, the radio's got to switch the groups, talk to different clients. There's more SU that comes into the picture. But when I first got this chart, and we've got data obviously that goes well beyond this, but this is when I really started to get excited, right? Like, wow, the same setup that we were getting 300 before, I can now get 800 plus in. Keith? No, that is not the trend. Oh, sorry, you're asking this. Oh, does it? Yes. The question is, does the MU line cross the SU line? The answer is absolutely yes. The question is where, and we are working hard to push the crossover point much further out. Yeah. Percentage of data loss on UDP, well, pretty high because we're driving the channel. We're overdriving the channel, so any UDP test is going to have lots of drops, right? Yeah. Sorry. Okay, these are single stream devices. Yes. Oh, yeah, correct. Yeah, so the question is it an apples to apples comparison because it's SU here, but it's not necessarily, you could do a three-stream case. I would tell you this is completely apples to apples. It's one stream to one, within the one stream class, this is totally apples to apples, right? If I have three single stream devices that have data to send, that is all I'm going to get on that AP, right? But with MU, they can go concurrently, right? Or actually, it's the other way around. It's downstream MU, but you take my point. So no, this is absolutely structured to be apples to apples, right? I concede that obviously we have devices with higher order stream counts, but then you would expect to see multiples there. I could show you two stream, right, with two stream MU, and we would see another jump. Right? Let's take it off. Tell you what, let's take this offline. Yeah, but it's apples to apples. Okay, efficiency. So this might start to get into some of what you were just asking about. So here are some big sort of background questions. So where do the savings come from, right? Why are we getting these gains? Why isn't it a multiple, right? So if it's 3, why isn't it just 3x? Why is it 2 point whatever, or in the two-stream case, it's 1 point, whatever. What factors affect the ratio? What is the range of gains? Is SU ever more efficient, right? In particular, again, this is something that was interesting to me in high-density environments. And would we ever not recommend MU, right? So just all kind of fundamental questions that we kind of set out to answer. So you've seen these charts from me before. So here is an airtime breakdown of the throughput test that we just saw. So if I have 3 one-stream stations, I have basically, and they all, I'm trying to send to each of them, I've got 3 TX ops, right, where the AP has to get the channel, right, so it has to arbitrate, and then go through that whole sequence with CTS, ACK, and block ACK. So these are the 3 TX ops. In this case, this is a very simple example, a very unrealistic example. This is just, I'm assuming that there's a single TCP ACK in each of these TX ops, right? So just one 90-byte payload, right? So it's very small. We'll look at some other versions in a minute. So here's the equivalent MU trend. Have a look. Okay, testing. Oh, great. Okay, so so the MU is up above. So it's basically 600 some odd microseconds versus 390. And here's where the deltas come from. So this is, that's the whole package. There's the payload, right? And of course, there's only going to be one because it's shared. And just on a straight airtime basis, this example is 1.63 times more efficient. And if you break it down, this is what goes away, right? So I give up the 2 arbitrations and the CDS. I give up the interframe space and the preamble that goes into the payload. And of course, I don't have the payloads. The other 2 things are fixed in size. They're always going to be the same amount of time except for the arbitration period, which can vary a little bit. But the payload, of course, is going to be highly variable. And that's one of the big deltas in terms of how efficient it gets. And again, we're going to look at some other examples here in a minute. Then I have to add back my block ACK requests in the MU case because now I have to pull the stations to get the ACKs, right? So there's a net add. So when you do the balance sheet, if you will, for airtime, you end up with some savings and so you save some time, you get some time back. So that's the whole thing. So here it is with a little more realistic example. So here's a aggregate of 32 TCP ACKs, SU on the bottom, MU on the top, and now it's a slightly more efficient, 1.7 times more efficient in terms of airtime. Again, ACKs are small, but normally we do see, if you're doing a file or something, you're going to have lots of ACKs in a single TX op. So this would be more representative of what you'd see in the real world. So let's look at some payloads. So here is 96K downstream transmission. And here's the MU equivalent. And now it's 2.5 times more efficient. Again, just on a pure airtime basis. And of course, there's no retries in here. I'm assuming a clean channel, maximum rate, and so on, right? So it's contrived, but just to kind of start to walk you through where the savings come from. Now here's a 2-stream example. So kind of the question you were asking earlier. So in this case, it's about 1.7 optimally with this size. And you can have bigger payloads, right? The standard allows for even bigger transmissions than this. But that's approximately what it turns into. So we modeled the airtime against a whole range of MPDU sizes. So basically from 64 bytes on the left all the way across to 200 and almost 300K on the right. And the red straight up line here, you can't see so that's the equivalent SU airtime. And again, this is just a single TX op. So this is one transaction, right? We're not looking at the whole file transfer, chariot test, or whatever. And then the green line is the MU equivalent time, and then the orange line is some amortization of the sounding overhead. And that's a model, again, on a single TX op. And basically, the takeaway from this slide is there is no frame size for which MU is not more efficient, right? Or said differently, SU is always less efficient, or SU will always take more airtime than MU, regardless of the packet size. And the bigger the packet size, the bigger the payload you're trying to get across, the more efficient MU will be. Okay, so single TX op, we're assuming the groups are full, clean channel, and so on. So these are idealized, but again, just to sort of help you understand. So coming back to those questions I asked, so what exactly are the savings? We take out the arbitration, the CTS, the extra AMPDU, and the preambles. We offset that by adding back in some bars, basically. The reason MU good put is not simply a multiple, the reason it's not 3x instead of 2 point whatever, is that I'm adding back, right? The costs, there's some losses, but there are also some gains, and the size of the payload really matters. Efficiency ratio is also affected by spatial stream count. So the ranges are, it's about 1.6 to 2.5 for single stream devices, depending on the size of the payload for a particular transaction. And for 2-stream devices, it's about 1.7, up to 1.7. It's always going to be more efficient, and My conclusion is MU ought to be turned on in virtually every environment that most of us work with on a daily basis. Stadiums over 20,000 seats are kind of a TBD. Not sure about that one just yet. There's some other reasons to think maybe that isn't a good idea. Okay, sounding overhead. Okay, so I showed this earlier, but so this is the sounding process, but we can start to ask a lot of questions about how this works. So the NDP announcement, well, how often is sounding happening, right? That's obviously a key driver of the amount of sounding load. How big are the feedback frames? And what rate do they go at? That's also very important. What rate is all the control frames going at? What percentage of my feedback frames don't make it in the first place, right? Either because the client never heard the poll, it missed the NDPA, and so it didn't even send a measurement, or attempted to send the measurement and there was interference on the channel, right? Because they're pretty big frames, right? So failures there will have a big effect. And then what about PSS interference, either Wi-Fi or non-Wi-Fi interference? So you start to look at this exchange, there's many things that can go wrong with it, right? And the examples I was showing you with perfect MU and so on, I mean, these are, again, clean lab conditions. We're not challenging the sounding process. So I'll blow through just to give you some sense of how complex this is. These are, again, called compressed beamforming action frames, and this is the measurement that the client takes and sends back to the AP. This is all in the standard and in the CWAP book. But this is basically a breakdown of the frame. And to estimate the sizes, I'm going to just go through this super quickly just to mostly show you how crazy complex it is. So this is the formula. So it's the number of chains on the client, right? Because each chain has to sense, right, what it heard. This is the number of subcarriers, so you have to report on each individual subcarrier for each chain. This is the number of angles that are being measured for each subcarrier. This is the precision of the measurement, right? So if you think about the number of subcarriers, right, hundreds and hundreds of 80 megahertz channel, it gets pretty big. And that was just all that is also true, also present in an SU sounding frame. And then for MU, there's an additional report that's tacked on the end with what are called delta SNRs, right, that make it even a little longer. So that's how you get to 1,499 bytes. Very easy math. Exactly. So trust me, I'm going to fly through this. Trust me, the math works. But here are we tied it out so you didn't have to. So here is 80, a 40, and a 20. The good news is that the sounding sizes, the bandwidth gets smaller. I have fewer subcarriers, right, that I'm sensing. So I'm not having to report as much data back to the access point. The bad news is, because the bandwidth is smaller, my MCS 0 is a lower and lower number. So from an airtime perspective, it almost is, it's virtually the same. It's just plus or minus 10 or 15 microseconds in this example. So it takes about the same amount of time. So here is a airtime model of a sounding exchange, and it's about 1,500. So it's 412 microseconds per feedback. As I just said, it's relatively independent of channel width. So all the ones together are 1.2 microseconds, and the entire exchange is 1.5 milliseconds, right? That's an eternity, right? If you're used to Wi-Fi timing, right? That's 15. Well, sorry, but it's a long time. So anyway, sounding intervals. So you can measure this yourself. It's really easy to do. So what you do is you filter your packet capture on broadcast NDPAs, right? Not directed NDPAs. Those are used for SU sounding. You use broadcast NDPAs. And you just look at the delta T. So this is a chart of the delta T of a packet buffer with that filter applied. So you can obviously see here the interval between the NDPAs is more or less about 40 milliseconds. This is with a 3-station chariot test. Okay. Yeah, so the question is, in effect, do we control the sounding interval? Right? Is it configurable, or if it's not configurable, is there anything we can do about it? The short answer is no. You can't. We can potentially. Our radio vendors can, and we're working with them. Right. The early approaches, as I'll say in a slide coming up, is they're conservative. The algorithms are very conservative right now because it's brand. Is it dependent? Yeah. If we found that it's dependent on the number of stations, the answer is absolutely yes. So here's 10 stations with a moving average. So you see the jitter, right? There's a lot more jitter. Here the jitter was about 8 milliseconds, right? So here it's significantly higher. So this is a 10-station test. All right, and now the moving average is down between, it's around 15 milliseconds after we get through the training interval. So significant acceleration of sounding. And that's for a couple different reasons, one of which is that because the radio is it's changing which stations it's speaking to, right, from transaction to transaction, it's probing the channel much more often. Yeah, John? These are stationary points. Yes, yeah. We've not looked at mobile clients yet. These are all fixed. Yeah. How often are you doing the sounding prep? How often is it triggering figure out what the client? So this is the interval. 15 milliseconds. Yeah. So this is so every time there's an NDPA, that is the beginning of a sounding exchange, right? So this is a direct measurement of the interval, right? Did we use the HP smart rate on these? Yeah. So another reason we went with OneStreams for this particular set of tests is that we were underneath a gig. The smart rate is not available on the APs yet, so we were limited. We were using lagged APs. But in the future, that's something you might do. Right. Huh? I'm sorry? No, the 325 doesn't have smart rate. But yeah, let's take in Keith's spirit, let's take the vendor stuff offline. Yes. Is the sounding interval linear or exponential? Sorry, you meant sounding size or interval? Yeah. Yeah, okay, so the question is it grow, basically? So hold that question and I'll answer it next here. So this is the training period, right? We've got less MU, then the MU picks up. Okay, so what happens when we have multiple APs on the same channel? This is sort of a way of answering the same question that you were asking. So I'm asking this question because of the high density case, right? So in an arena, typically you're going to have 5 to 10 APs per channel. In a large stadium, you're going to have 50 to 80 APs per channel. So you might have noticed in the photo earlier, there were multiple APs on the ceiling. That was to do this particular test I'm going to tell you about now. So we set up 5 APs and we put 3 stations each on them. And again, we are intentionally taking out, we only want one AP, we don't want it thrashing clients, right? We want to have just pure MU groups on each one. The purpose of this test is to look at how channel sounding scales at the channel level, right, with multiple APs. So here it is. Here is the same chart we were looking at earlier with, so this is AP1, AP2. So it's a 6-station test with 2 APs, right? And again, each AP has 3 stations on it, right? But they're going at the same time. So you can see now it's about 60 milliseconds. So before we saw 30 milliseconds, right, with the 3-station test. So now it's about, or sorry, I said 40 milliseconds of the previous test. So now it's about 60. So it's actually slowed down, right, individually, but at a channel level, right, if each AP is going at 60, then that means that the channel as a whole has to be going a lot faster, right? And so here it is, and if you're not familiar with CDF plots, I apologize, but this is really the best way to look at this. The 2 lines here, that's basically saying 60 milliseconds. And one way to read this chart is that 80% of the sounding exchanges have basically a variation of about 18 milliseconds in this case. And then the dotted line, this is the aggregate level, and you can see there that it's around it's 30 milliseconds at the 70th percentile. So it's about at the channel level, it's going twice as fast as the individual APs are going, right? So let's scale it up. Here's 3 APs. Now you can see that it's starting, whereas here it was pretty tight, right? They were all, each AP was able to get at the channel when it wanted to sound, right? So now we're actually seeing the sounding intervals really push out. So it's about an 8x increase in range in terms of the delay between the sounding intervals at the 80% mark. We are seeing good fairness. So there's a whole new concept of fairness, right? So it's not just station fairness. Now we have sounding fairness we have to worry about. But we're seeing good fairness in this case. And the aggregate, so this comes back to the question that was asked here earlier, is what is the limit, right? So you'll notice that this aggregate is pushing up and to the left, right, as we add more stations. So basically what I'm doing is I'm adding sounding overhead to the channel, right, intentionally. And then here it is with 5 APs. And again, if I just, I'll flip back and forth a couple times. If you look at that dotted line, right, so it's pushed up even higher and to the left, and you can see that it's plainly approaching a limit, right, of, call it 12 to 15 milliseconds. Now at a per AP level, we've pushed out. It's the 80% are now spread across 170 milliseconds, and the fairness is breaking down. Right, this is not payloads. This is we're just looking at sounding traffic. So, what do we conclude from all this? So the sounding frequency does increase with the station count, right? Because it's got to talk to, things are changing more rapidly, and the AP has to update itself more quickly. For the high density case, the overall frequency speeds up while the individual APs are decelerating. We don't yet know the answer to this question, which is what is the effect? Do I get less MU if I need to sound every 40 milliseconds to do MU, and I can only get it every 60 milliseconds? Right? Is there going to be some impact, right, in terms of the AP's ability to choose MU, for instance, right? We don't. So that's an example of stuff that we're all learning how to figure out, and every vendor is going through this, right? So all my colleagues are sort of working on the same problem in the lab. The reason for the 12 to 15 milliseconds is that starts to approach the length of a TX-op with sounding, right? So it doesn't make sense. You would never push any further left than that because you're bumping right up against the payload size, right? So that does make sense as well. So that does imply that there is a limit to the number of MU APs you can put on a channel, and this is why I'm still sort of undecided in the high density case. The very high density case. And again, I'll reiterate, the first generation algorithms are conservative. As I said earlier, these numbers are going to get even better. Again, we're disclosing this information today because this is an audience of very experienced, fairly senior practitioners, and we want to start building. We need to start sharing what we're learning with you so that you can adopt these products. And I think it's good for the industry to put this knowledge out there, right? Bear with us. All the vendors are going to every optimization we can make, we will be making. Yeah. Yeah, so the question is, were all these APs on the same channel for this test? And the answer is yes. That was explicitly the target. Did we try it on different channels? No, but I would expect that that would just look like the ones that I showed earlier. Okay. Okay, so just to close out, I know it's been a lot of content for early in the morning, but just some thoughts. So based on all that, we did this in about a month in the lab. And so based on that experience, so basically I would tell you, I don't think MU should affect, as you're working on designs, again, some of you are supporting your own, you work for a company in IT, some of you are integrators, some of you are vendors, and so on. So, but as you're working on designs for whatever context, I would tell you today that I don't think MU really affects the AP counts, the same rules that we've been using for a while now, the 1 AP for every 250 square meters or 2,500 square feet. I think that's still about right. In general, you can go a little denser than that if you're trying to bump up the rate. But basically, whatever methodology you're using, I would tell you probably don't need to change it, as long as you're at least that dense. Doesn't really affect AP placement. Again, we're seeing there is some sensitivity to the position of the clients, but it's not, I mean, I'm getting these results in a linear mode, so we're not seeing anything that would tell me that you needed to, like RTLS used to be in the hospital space where you had to have perimeter APs and all that sort of stuff. Right now, I don't think that there's any special design requirements. And probably the best way to think about it is that MU makes an AP potentially more efficient or able to kick a little, provide a little extra service if there are MU stations in the environment. Of course, that's, as always with a new Wi-Fi generation, the stations are always lagging the infrastructure, so it's going to take time to get these gains. But MU is a bonus, I guess. It's not the baseline. The baseline is the SU performance, and then to the extent that you get additional on top of that, you want to sort of pave the way for those gains as the clients get out there. And then finally, so what about high density environments? So 20 meg channels should still be used. All the reasons we've talked about in past sessions remain true. Based on the data I've showed you, with the current generation firmware and software from the vendors, I'd tell you that there's probably an upper bound of somewhere around 5 APs on the same channel. That may go a little higher in the future. Again, I reserve the right to change this number, but based on what we're seeing right now, I'd say it's around 5. So if you do the quick math, and our capacity planning methodology for estimating clients is out there on the web, you can Google it, but if you just do some quick math, so 5 APs at 150 users per radio is 18,000 associations. Right? And then if I just cut that in half to be conservative, because not everybody's going to be near the AP, and so the rates are going to be distributed and so on, that would tell me that I am safe to do MU and should be doing MU in environments up to about 10,000 seats, right? So lecture halls, right? Amphitheaters, auditoriums, you should be, if you can, if the customer will pay for it, you should have no hesitation in deploying MU equipment into those environments, and you potentially will see some gains. And then last but not least, I've talked about rates several times, but bringing those rates up is important, not just in high density, but I think this is going to become a best practice actually in enterprise environments, just to, again, reduce the airtime hit of all that extra SU traffic, so we leave more time for MU. Yes. Sorry. Manual versus automatic what? Oh. Sorry. When I say sorry, I had to reread the slide. So when I say manual, what I mean is trimming the rate. So the default configuration out of the box for all the vendors, you're going to have you're going to have all the rates enabled, right? And in particular, I'm talking about the OFDM rates, right? So the 6 through 54 megabit numbers, which are what are used for the control frames. So you want to, what I'm saying is you want to delete 6, 12, 18. You want to start at 24. If you have issues, so that can create interop issues, or at least it used to in certain environments. Usually that's if you've got like scanning, handheld scanners and that type of thing. But for typical, smartphone, tablet, laptop devices, that's a very, very safe thing to do, and it will potentially give you some more performance. Any other? You talking about MU specifically? Yeah, so the question is, basically, if you had the option to, if there was an MU on-off switch, right, would you ever turn it off? Again, that was really one of my basic questions when I started this whole process, and my short answer is no, I would run it on by default.
And Chuck, that's all the way down into G rates.
Yeah, lower MCSs. Yeah, and so this is something else. There's so many algorithms now that are in the radio. One of the algorithms, right, the radio is making a decision on literally a frame-by-frame basis about whether to do MU or SU. So it's actually going to decide for you, does it have enough data buffered, for example, to make MU make sense, right? And then does the channel support it? Do I have current sounding information and so on? So and you saw a little bit of that earlier with the Chariot example I showed where you saw a little bit of SU stuff. So the radios generally are going to do this and work it out. Sam?
Can you quantify the airtime impact specifically without having those lower data rates disabled? Can you tell us for each data rate exactly, or get us close to what the actual impact is and where the efficiency ultimately falls on?
Yeah, good. So the question is, can I quantify the basically the amount of airtime consumed by the exchange at different control rates, right? 6, 12, 18. Haven't done it. We could build that table, but I would just go straight to 24. Yeah. Yeah.
So you don't trend to lower the basic rate if, let's say, the control frames are at if the control frames are at 6. Do you expect the efficiency to go down drastically, or the same?
So the question is, if you leave it at 6, if you don't modify the rates, is it going to be really harmful? It turns out, no, it won't be really harmful. You just won't get, the gain will not be as high, right? Because the amount of SU traffic does increase proportionally to the amount of MU traffic, or you could even argue at multiples of the MU traffic. So it's to get that back or to offset that hit, that's why we raise the rates.
So TX operations from the AP to the client, is there any effect, negative or positive, on RX operations?
From station to AP? Yes. Yeah, so the question is there any effect on, what does this do on the upstream from the station back up to the access point? That's just straight SU. There's nothing in wave 1, or sorry, in wave 2, it's pure, multi-user MIMO is pure downlink. So all the upstream communication would be standard wave 1 or.
Right, but the increased sounding interval things with the longer sounding periods, that may have any effect on the upload.
Oh, sorry. Okay, I misunderstood the question. So he's asking a different question, which is, if I've got all this extra overhead on the channel now, what is that doing to my upstream traffic, right? So the answer is, as you saw with the downstream traffic, anytime it's more load on the channel, right? So every station has to compete for airtime, and there's more competition, so there may be less available. It depends. I think for most loads that you're going to see in enterprises and hospitals and a lot of the environments we deal with on a day-to-day basis, probably you're not going to see a limit. You start getting into the lecture hall, auditorium type scenario, that's really why I did those scaling tests I showed you. And yeah, then you start to hit the capacity limits of the channel.
And then I've definitely seen the value of this for TCP operations and one down, but as far as VoIP, you said 50 clients per AP with the 20 millisecond, 30 millisecond UDP packets. Is there a cell limit for VoIP?
Yeah, great question. So what about voice traffic? We've not studied it. Again, I'll go with the answer I just gave. Again, I think in most voice is done in those enterprise and clinical environments where the duty cycles are not that high to start with. So I think if anything, this is probably, you'd have to have a MU capable voice handset, right? First of all, but.
Let's say you've got just an MU capable handset, but you got a bunch of MU capable other stations.
No, I understand, but it's two scenarios, right? So it's SU only phones, and then there's a future where we might have MU handsets as well. Yeah, I think in those environments, the duty cycles are low enough that the incremental MU is, at the end of the day, basically what this is showing is that MU is ultimately helpful for getting back airtime. So something we really didn't talk about is to the extent that so if all stations have the same amount of data to send, with MU, I can clear that data quicker, right? So potentially, I'm actually getting airtime back for those other clients if the MU stations are clearing their buffers, right? So there's an argument to be made that it's actually helpful for SU devices, right? So okay, one last question. So I think the question is, did we move the stations? Yeah, so the question is, have we tried to move the stations around? Not yet, with the exception of taking them outdoors, because we needed to get out of the lab for a little bit. No, we've not tried any mobile cases yet. We haven't looked at Doppler or any of those things. It's just, we're just starting, we're just learning how to drive the car just like you are. Yeah, so anyway, thank you very much